Alright, in this video we are going to talk about entropy as well as how to calculate Gibbs free energy and what all that means. So entropy is the measure of energy dispersal in a system. This comes back to the second law of thermodynamics, which is that energy always tends to disperse or to spread out in a system. A word commonly used is disorder, that it always tends to become more disorderly, which some people like to use that word more than others. And ultimately, in nature, things tend to become more dispersed energy-wise. It tends to spread itself out. So entropy values are typically looked up. They're in a reference chart, so it has to be given to you in some form or another. A negative delta S value means that we're becoming less disordered or more orderly. We're putting the energy back together, if you will. An example, easier to think about an example of what actually is happening is going from liquid to a solid. The atoms are much more structured in a solid substance than they are in their liquid form. They don't have as much space to move around, and it's much more aligned. A positive delta S means that entropy is increasing or energy is dispersing. And the example would be going from a liquid to a gas or from a solid to a liquid. So changes of state this way are positive in entropy change versus the other ones are negatively entropy changed. We have some entropy guidelines as far as when should you expect it to be positive versus negative. The entropy of a solid is always less than the entropy of a liquid versus a gas. Increasing the number of particles or moles increases the entropy. So what does that mean? If we have a balanced chemical reaction, so let's make water. We have 2H2 plus O2 goes to 2H2O. On this side of the equation, we have 2 moles plus 1 mole. So we have 3 moles on this side, and it's going to 2 moles. So looking at this equation, we are going from a total of 3 moles to 2 moles. So we're decreasing the number of particles, which would decrease the entropy. Entropy increases when temperature goes up. Kind of makes sense because molecules and atoms are moving faster. And then making a solution. So anytime you see AQ, it increases the entropy. So if you took salt and dissolved it in water, there would be a higher entropy after you've dissolved it as opposed to before dissolving it. There we go. Alright, so ultimately, why is that important? Gibbs free energy is represented by this equation. Delta H is something we've already been talking about. It's the change in heat or the change in energy or the change in enthalpy. They all mean the same thing. Minus the temperature times the change in entropy. So entropy and enthalpy, if you're not listening very carefully, might sound like the same thing. Enthalpy is really the change in heat for this class, whereas entropy is talking about energy being dispersed. This equation, delta G, ultimately what it tells us is whether a reaction is going to happen spontaneously, meaning on its own, or whether it won't happen spontaneously. So this equation is quite important to chemists because with this calculation it gives you an idea of whether or not a reaction will actually occur. It doesn't tell you anything about how fast a reaction will occur. It just says it might happen. So it could take a second or it could take 10 days. Kinetics talks about the speed of reaction, and that's something that we will get to later in the semester. So I've already defined these variables. A negative delta G means it's a spontaneous reaction. It'll happen on its own, versus a positive delta G means that it won't happen spontaneously. Typically, we like to know if something is going to happen on its own or not. So typically, a delta H that's negative and a delta S that's positive will result in a negative delta G. This is just math. If you want to plug those numbers in, you can find that out for yourself. And that means that you'll have a spontaneous reaction. If you have the opposite values for delta H and delta S, that means that it would be non-spontaneous. If you end up with something like a positive delta H and a positive delta S, or vice versa, it really depends on whether the temperature is high or the temperature is low, on whether the delta G value will be overall negative or overall positive. So those scenarios you might actually need to plug the numbers in to see, or if it's asked for you to calculate delta G. So, for our example, when graphite reacts with hydrogen gas at 300 Kelvin, delta H is minus 74.8 kilojoules, and delta S is negative 0.0809 kilojoules per degree Kelvin. Actually, it's just Kelvin, excuse me. It wants to know if the reaction will occur spontaneously. So we have to do a little bit of math to see. So delta G equals delta H minus the temperature times delta S. Delta H is negative 74.8 kilojoules minus a temperature of 300 Kelvin times negative 0.0809, and our units are kilojoules over Kelvin. One thing to keep in mind for delta S is the reference tables for delta S are typically given to you in joules per Kelvin as opposed to kilojoules per Kelvin. So that value almost always needs to be converted to kilojoules per Kelvin in order to subtract it from the delta H value. The reason it's given to you in joules per Kelvin is because the delta S value is typically a decimal number. It's a very small number if you represent it in kilojoules. I converted it already to make this problem a little shorter. Alright, so now to do this math out, we have minus 74.8 kilojoules, subtract 300 times that value, comes up to be negative 24.27. Kelvin divided by Kelvin cancels out, so now your units are kilojoules. We can subtract a kilojoule from a kilojoule, or actually in this instance, we're going to add, since we're subtracting a negative number. Negative 74.8 plus 24.27 ends up in a negative 50.5 kilojoules. So our delta G is negative. Based on the fact that it's negative, it will happen spontaneously. It would happen on its own. As far as delta G, more specifically, as far as a better understanding of entropy, if either one of those seems ambiguous to you, or if you're just interested in more, the link on the bottom of this slide brings you to a YouTube video which does a pretty nice job of explaining it more in depth than what I'm doing. So that is up to you if you want to watch it. All right. Thanks. Bye.